Okay, now we take a look at a chain rule example where we start with a function f of two variables x and y, and then in turn each x and y are also functions of two variables s and t. Okay, so ultimately we want to find the partial derivative of f with respect to s, and also the partial derivative of f with respect to t. And then so for each of them we have a separate chain rule described above here, and in using the two chain rules we're going to need all the possible different partial derivatives. So let's write them down first. So first, the partial of f with respect to x. So we're thinking of y as a constant. So here we need to use the chain rule. So the derivative of the exponential function is the exponential function, and then differentiating inside. So we're differentiating with respect to x. We think of y as the constant coefficient, so the derivative would just be y. So let's rewrite it with the y in front. So you got y e to the xy. And now the partial derivative with respect to y is similar, right? So the derivative of the exponential is the exponential, and then differentiating inside, x is now the constant coefficient, so we have times x. Okay, so now let's look at x. X is a function of two variables, so we have two partial derivatives. So we have the partial derivative of x with respect to s. So here, the sine t we think of as being constant. So the derivative here is just 3 sine t, right? Because we're just thinking of the function as some constant times s. And then similarly, when we differentiate with respect to t, so the 3s is just a constant coefficient, and then the derivative of sine is cosine. And then now we differentiate y with respect to s and t. So y with respect to s, so the 4t squared is the constant coefficient. And then the partial of y with respect to t. So s is constant. And then the derivative of t is, the derivative of t squared is 2t. Okay, so we get the partial with respect to y of y with respect to t is 8st. Okay, so those are all the different partial derivatives, and so now let's first look at the partial of f with respect to s. So the partial of f with respect to s. So I'm just going to rewrite it in terms of the subscript notation, right? So it's the partial of f with respect to x times the partial of x with respect to s plus the partial of f with respect to y times the partial of y with respect to s. Okay, so now just collecting all the correct terms, right? So f sub x is this expression here, so y e to the xy times x sub s, which is this 3 sine t, and then plus f sub y is this expression here, so x e to the xy times y sub s, which is 4t squared. Okay, so just like before, I still have the variable x and y floating around, so I want to write everything in terms of s and t, so that this should be this should be a t. So I need to plug, so x is equal to 3s sine t, and then y is equal to 4st squared. We need to substitute that back in. Okay, so let's do that. So y goes here, and then x and y go here. So what do we get? So let me start from the left side because I'm going to need a lot of space. Okay, so we get 4st squared. So that's the y, and then the exponential x times y is 3s sine t times 4st squared, and then times 3 sine t. Right, so that's this expression here that doesn't contain any x or y. And then now plus this expression, so x is 3s sine t times the exponential. So you have 3s sine t times 4st squared, and then times 4t squared. Okay, so I get this whole thing here. So sometimes in these examples, you get quite long expressions. So usually in the MyOpenMath homework, a lot of times you can just leave everything like this. It'll accept this as correct because it's equivalent to the correct answer. So there's not usually a need to simplify any further. But if you want to simplify, there are some things we can do here, right? So I can multiply this out, and I can also bring this in front, right? So 4 times 3 is 12, and then I have st squared times sine t, and then the exponential, so multiplying up top, so 3 times 4 is 12, then I have s squared t squared sine t. So that's the first term, and then the second term, again I multiply this and this, so you get 12 st squared sine t, and then exponential, so just multiplying that out, you get 12 s squared t squared sine t. Okay, so we get that, and then if you compare these two terms, they're actually exactly the same, right? So 12 st squared sine t, and the exponential is also the same, so they're like terms, so I can just combine the two. So you get 24 st squared times sine t times exponential 12 s squared t squared sine t. Okay, so for this one we can do a little bit of simplification, but again, usually it's not really necessary. You can just leave it like this. Okay, so that's the partial of f with respect to s. So now let's take a look at the partial of f with respect to t. Right, so the partial of f with respect to t. So the chain rule formula is going to be the partial of f with respect to x times x sub t, and then plus f sub y times y sub t. Okay, so now let's try plugging everything in. So f sub x was this thing, so y e to the xy. X sub t was 3s cosine t. and plus f sub y was x e to the xy, and then y sub t was over here 8st, and then again I have to plug x and y back in. So let's just quickly remind us what was x. X was 3s sine t. And what was y? Y was 4st squared. Okay, so we plug that in. Okay, so what do we get? We get f sub t is equal to y, which is 4st squared e to the xy. So I'm just multiplying this in the exponent. So you get 12s squared t squared sine t, and then this 3s cosine t, and plus x, which is 3s sine t, and then the exponential, which is 12s squared t squared sine t, and then times this 8st. Okay, so again, without any simplification, this is what you get. But if you want to simplify this, so what do we get? So 4 times 3 gives you 12, and then we have s squared t squared cosine t exponential 12s squared t squared sine t, and then plus 3 times 8 is 24. Then we have s squared t sine t, and then the exponential. Okay, so this is what we get for the partial of f with respect to t.